YouTube recording for Chapter 8, which is called The Role of Stability in Weather. And this is the first of 4 chapters that we're going to be following that actually is going to take us on a pursuit from discussing atmospheric stability primarily in this PowerPoint presentation to moving on to eventually discussing thunderstorms, severe weather, and tornadoes. And so between chapters 8, 9, 14, and 15, four separate chapters, we're going to move from the basic building blocks of atmospheric stability and its discussion all the way to tornadoes. So let's lower the textbook. I just wanted to show that to you and start our PowerPoint presentation. So let me just begin our slideshow. All right, so what I'm going to be doing is just starting with a basic discussion of vertical motion. So we've talked about vertical motions already in the context of convergence and divergence and upward and downward motion. And so what we're going to do here is going to just begin with just a reminder of our large-scale vertical motions. And so large-scale vertical motions can be caused by upper-level convergence, which leads to downward motion in high-pressure centers, like the one we have centered here in North Dakota. And upper-level divergence can lead to upward motion in low-pressure centers, like the one that we have centered just to the west of New York State. And we have another one down here in Texas. And so this is basically 2 major ways that we get upward motion. And the third way that we get vertical motions in the atmosphere, particularly vertical ascent and upward motion, is through mechanical lifting along frontal boundaries. And so along cold fronts, warm fronts, stationary and occluded fronts, we also get upward motion. And this is caused by what I like to call mechanical lifting. And this is where in some way, shape, or form, cold air forces warm air to rise. Now, in each of these situations when we're talking about highs and lows and fronts, the air is actually being forced to rise or fall based on large-scale motions. And the density of the air is not really a big factor, although it is with fronts a little bit. But the air, what I want to make clear here, doesn't just rise on its own. There's something that's actually causing the air to rise rather than just basic density differences and buoyancy differences that might cause upward and downward motion. Now what I have here is a map of the United States from the 7th of October 2022, and this is of the United States. And what I'm showing here in this map is vertical motions. So vertical motions in atmospheric science, we use a quantity called omega. And what omega does is it measures the rate at which pressure changes over some sort of a vertical distance. And we measure omega in this particular case in decapascals per second. And a decapascal is 1,000th of a millibar. So if you take a look at the legend, you can see that our decapascals basically for the most part are basically anywhere from about plus or minus 10 to 20 decapascals per second. So we're talking about maybe 1 to 200ths of a millibar per second. So what I want to point out here is that when we're talking about large-scale vertical motions in the atmosphere, these are really, really slow rises and falls of air. We're talking about vertical pressure changes. In better words, changes in pressure on the volume of air that result from the air rising through the atmosphere or sinking in the atmosphere on the order of thousandths to hundredths of a millibar per second. So we're talking about really small changes, very slow upward motion and downward motion. Now, because pressure always decreases with altitude, what we see is that omega is less than 0 for upward motion. In better words, pressure decreases as air rises. So negative omegas on our map indicate upward motion, and positive omegas indicate downward motion. And so you can see again that the motions are relatively subtle. They're in thousandths to hundredths of a millibar per second. Now, when we actually get thunderstorm activity along an advancing cold front, which is what we have here, and this is actually a map from the 13th of October 2022, and this is actually a forecast map. I wanted to find a map that actually indicated thunderstorm activity. And what you can see right here on this particular map is an indication of predicted radar reflectivities, and you can see that these are pretty large reflectivities, and these indicate forecast thunderstorm activity along a cold front that's plowing through from Iowa southwestward through Missouri, Oklahoma, and Texas. If we take a look at the actual, let me continue on with this. So we have intense convection along a front. So now we have air that's rising, not just as a consequence of a cold front forcing the air to rise, but this is rising air that is also most likely as a result of warm, buoyant air ahead of the front that's being given a kick by the front itself. So when we get convection, really intense, deep convection, this is driven by density differences in the atmosphere. And we also see that when this occurs, we got much larger vertical motion. So if you take a look at the reflectivities, basically from northeast Missouri and down a line from this point southwest through Missouri, Oklahoma, and into the northern part of Texas, you can see some omegas that are on the order of 50 to 60 decapascals per second. So these are pretty large upward motions. If we take a closer look and we just kind of move onto our vertical velocity map and focus in on the southern plains, you can again see that we have some centers that are forecast of vertical motion on the order of 60 decapascals per second. So this is actually greater than 0.6 millibars per second. So this is actually quite rapid, quite vigorous upward motion. And so what I'm going to be doing, and what I'm going to be doing in this lecture, and then for the next 3 chapters after that, is moving us away from, for the most part, large-scale vertical motions that are forced by highs, lows, and fronts. And then I'm going to be just focusing on vertical motions that are a result of density differences in the atmosphere. So let's actually begin this conversation by just focusing on our atmosphere and the fact that we've been taking a look at pressure gradient forces already in our class. We've talked about pressure gradient forces at the surface. We've talked about pressure gradient forces at upper levels, but these have all been horizontal pressure gradient forces. And what we see on the horizontal is that pressure and height actually varies quite gradually over horizontal distances. And so we actually see that we don't get big changes in pressure over horizontal distances. This is very different than what we see in the vertical. If you remember from earlier conversations, particularly when we were talking in Chapter 7 about the atmosphere in the vertical, what we saw in Chapter 7 is that pressure, which always decreases with height, decreases exponentially with height. And so in fact, we lose the first 500 millibars of pressure or weight in the atmosphere in the lowest 5.5 kilometers of the atmosphere. So pressure changes very rapidly over height. And so we actually have a very tremendous vertical pressure gradient force, which is pointing from the surface outward to space. And so this leads to kind of an obvious question if you think about it, and that is, why does our atmosphere just not fly out to space with the pressure gradient force being so large and directed straight upward? And the reason is, as you can see here in this figure, is that the vertical pressure gradient force is actually balanced by the downward acceleration of gravity. So the atmosphere actually stays in place because we actually have this balance between our vertical pressure gradient force and the downward force that we find when we actually multiply the mass of the atmosphere by gravity. The downward weight is actually balancing the upward pressure gradient force. So when we do get vertical motions in the atmosphere, they actually are quite small in contrast to the vertical pressure gradient force and the downward force of the weight of the atmosphere. So when we do get vertical motions in the atmosphere that are not forced by large-scale factors such as upper-level convergence and divergence in highs and lows and mechanical forcing as a result of fronts, when we actually just get vertical motions that are a consequence of a buoyant air or dense air rising and falling in the atmosphere, we get upward motions in convection as a result of the vertical pressure gradient force being a little bit greater than the weight of the atmosphere or gravity. And so when we have buoyant volumes or parcels of air, we typically will get air that just rises through the atmosphere a little bit. On the other hand, when we get downward motion, and we get downward motion as a result of convection, so again, as a result of these vertical motions that are caused by buoyancy differences, we get downward motion when the vertical pressure gradient force is just a little bit less than the impact of gravity on the weight of the air. And so this occurs when we have dense parcels or dense volumes of air. Now, I actually want to move on to a really important conversation, a really important topic in our class when we begin to move towards thunderstorms, and that is a formal discussion of atmospheric stability. I know that from time to time I'll talk about the atmosphere being stable or unstable, and not actually talking about what I mean by atmospheric stability. So I'm actually going to formally define stability in the atmosphere here in this slide, and then move forward with several other slides to describe how it is we determine the stability of the atmosphere. So the stability is determined by the response of an object after it's been displaced from its initial position. Now, before we talk about the atmosphere, I just want to keep this really simple. So let's talk about just displacing any object, like a ball or a marble, and just kind of moving it up or down the slope. So imagine that we displace an object from its initial position and that object returns to its initial position. So imagine we have something like a tennis ball that is actually caught in a depression like this. And we send the ball up the side of this little slope here. And what you'll notice, of course, is that gravity just pulls this ball right back down to its initial position again. So we actually define this as a stable system. So a system is stable when you displace an object from its initial position and the object returns back to that initial position. On the other hand, imagine we take this tennis ball and instead of putting it at the bottom of a hole or a pit like this, we actually put it on the top of a hill, and then we displace the tennis ball. Now, when an object is displaced away from its initial position, or it accelerates away from its initial position, in that case, the system is unstable. So now, just imagine that we have this tennis ball just kind of precariously balanced on top of this little hill here, and we give the tennis ball a little nudge. In this case, what will happen is that the tennis ball will accelerate away from its initial position down the side of the slope, and then it will just roll away. So the tennis ball won't return to its initial position. So we have an unstable system when an object, after it's displaced from its initial position, accelerates away from that initial position. And then finally, if we were to take an object and displace it from its initial position, and it neither returns to nor accelerates away from its initial position, what we see in this case, for example, if we just take the tennis ball and we put it on a flat tabletop or surface and we give it a little poke, what we'll see is that the ball will move as long as it has energy from that poke, and it'll just stop. So in this case, if we displace the object from its initial position and it just is going to stay to that location where it's been displaced, in this case, we say the system has neutral stability. It is neither stable nor unstable. It's just neutral. Okay, so let's talk about this in the context of something called a parcel. Now, a parcel, I'm actually going to define pretty formally here. In this case, I want you to imagine a volume of air that's the size of maybe a basketball or a volleyball or a soccer ball. So I'm not talking about an air mass here. I'm talking about a fairly small volume of air. And we're going to use our parcels to determine the stability of the atmosphere when we displace it upwards from the Earth's surface. Before we do that, before we actually begin moving parcels around, I actually want to define how it is that a parcel is going to interact with its surrounding environment. And this is actually going to be pretty simple to start with, and that's going to get just slightly a little bit more complex. So I'm going to define the parcel by 3 interactions with its surrounding environments. The first characteristic of parcels as they interact with the environment is that they're going to have flexible boundaries. So just imagine a balloon. Okay, so a balloon which you tie off, it has air on the inside and it's surrounded by its environment, and the balloon obviously can expand or contract. So the balloon has flexible boundaries, and a parcel, just like a balloon, is going to have a flexible boundary. So just imagine a balloon in this case. Flexible boundaries, it can expand or contract. Also, like a balloon, a parcel is not allowed to exchange mass with the surrounding environment. So when you blow a balloon up, you blow it up, you tie it off, and then the air inside the balloon is the air in the balloon, and the air in the surrounding environment is the air in the surrounding environment. And we don't allow any exchange of air across that rubberized boundary. So again, the parcel is just like a balloon. We don't allow any air to cross that boundary. There's no mass exchange with the surrounding environment. Now, the third characteristic that defines interactions of a parcel with its surrounding environment is different than a balloon. So in this case, we do not allow any energy exchange with the surrounding environment. So what we're saying here is that the rubberized boundary basically does not allow any energy to cross it. The energy inside the balloon is the energy inside the balloon, and that is going to be held as a constant value. Now, when I say energy here, I'm talking about the total mechanical energy, the air inside that balloon. So the total energy is equal to the sum of the potential energy of the air in the balloon and its kinetic energy. So the total energy, the sum of its potential and kinetic energy, is going to be a constant. We refer to boundaries that do not allow energy to cross them to being adiabatic boundaries. So an adiabatic boundary is a boundary that does not allow any energy exchange. And parcel boundaries are adiabatic. So in this case, like I just said a few moments ago, the total energy of the air inside of the parcel is a constant value. And it's equal to the sum of the potential and the kinetic energies. Now it's important to note that the potential and kinetic energy, those amounts can actually vary inside the parcel. So the potential energy can go up, the kinetic energy can go down, and vice versa, as long as the potential and the kinetic energy add up to be that constant amount of total energy inside the parcel. Now we actually create adiabatic boundaries, or we attempt to create adiabatic boundaries in our daily lives all over the place. So if you think of a refrigerator, the refrigerator is basically meant to maintain cold temperatures on the inside of that appliance. So the refrigerator boundaries with the kitchen, they try very hard to minimize or zero out the amount of energy that crosses the refrigerator to warm the air inside of it. In contrast, think about an oven. Ovens are hot. And so the boundary of the oven, what the boundary of the oven does is it tries to keep the hot air inside the oven and to keep it from being transferred to the kitchen to making our kitchen really, really hot. And of course, the insulation on our house itself is meant to keep the temperature on the inside of the house one value and keep that different from the temperature outside. So we're getting ready to go into winter here as I record this video, and in the summertime when it's hot, we also actually try to do something very similar in that we try very hard to keep the energy on the outside of our house outside of our house. So in the summertime when we air condition our house, we don't want that energy from the outside coming in and making our house hot. And during the wintertime, when we keep our house warm, we don't want that cold air on the outside. We don't want our house losing energy to that cold outdoor air so that our house gets cold again. So we really do try to create these adiabatic boundaries in our lives. And parcels, we're going to define to be adiabatic, and I'll tell you why that is in a few moments. But what we're going to see is that as air rises and sinks through the atmosphere, while we don't have balloons obviously going up and down in the atmosphere, parcels actually do approximate the way that air behaves when it rises and sinks in the atmosphere. So imagine that we have an atmosphere, and these little blue dots are meant to approximate atoms and molecules that comprise our air, and then we have these bubbles or these parcels that rise and sink through the atmosphere. Now, as a parcel rises through the atmosphere, what happens is that the pressure of the atmosphere on that parcel, just like the pressure of the atmosphere on a balloon, decreases, and so the parcel, like a balloon, will expand. Now, as the parcel expands, the distance between the atoms and molecules in the parcel will increase, and so the potential energy of the air inside the parcel will increase, and as a result, the kinetic energy of the air inside the parcel will have to decrease, so that the sum of these two quantities gives us our constant total energy inside the parcel. So what we see is that as kinetic energy in a rising parcel decreases, the parcel doesn't just expand, but it cools as well. So we get expansional cooling inside of our rising parcels. So parcels cool as they rise. And this is what we see in the atmosphere. And we've talked about expansional cooling in our class a little bit already. So what we see as a parcel rises is that the potential energy of the air inside the parcel increases, the kinetic energy of the air inside of the parcel decreases, and so the parcel cools. Now we can actually formalize the rates at which air in rising parcels cools given the three rules that we described in terms of our parcel interactions with the environment. So given that parcels are flexible, that there's no mass exchange with the surrounding environment, and that our parcels are adiabatic, we can actually define the rates at which air inside a rising parcel cools. And we're going to define these cooling rates based on whether the air inside the parcel is dry or subsaturated, or whether the air inside the parcel is moist or saturated. So let's start with dry air. The rate at which dry air inside of a rising parcel cools is called the dry adiabatic lapse rate. And we're going to use an uppercase gamma and a subscript d to indicate the dry adiabatic lapse rate. And the dry adiabatic lapse rate is just about 10 degrees Celsius per kilometer. And so what this means is that if you lift a dry parcel 1 kilometer, the air inside of that dry parcel will cool by 10 degrees Celsius as a consequence of expansion. So expansional cooling will lead to a rate of cooling inside the dry parcel of 10 degrees per kilometer. 10 degrees Celsius, by the way, is about 18 degrees Fahrenheit. And a kilometer is just a little bit more than 0.6 of a mile. So that's the dry adiabatic lapse rate. The next rate of cooling is called the moist adiabatic lapse rate, and so it's going to be uppercase gamma, lowercase m, and the moist adiabatic lapse rate is 6 degrees Celsius per kilometer. Now, in this case, we're lifting both dry and moist parcels through the atmosphere, but you see this difference in rates of cooling, and you see that the moist adiabatic lapse rate is less than the dry adiabatic lapse rate. Now, the reason for this is because as you cool saturated air, what happens is that some of the vapor in that rising air has to condense to form water droplets. And so you get condensation inside of a moist parcel as it rises through the atmosphere. So what we see in reality is that as you lift moist air through the atmosphere, you get a cloud. Now, that doesn't explain the difference in the lapse rates. What's actually going on while we get this condensation is that the water vapor, as it condenses, is actually releasing latent heat inside of our parcel. So as water condenses, the energy level of the water actually goes down. So as vapor, which is kind of high energy water, condenses to liquid water, which is more intermediate energy water, what happens is that excess energy in the water vapor is released to the air inside the parcel as the water goes down energy to form liquid water. And so that latent heat release actually warms the air inside the parcel a little bit. Now notice that we're not violating our adiabatic rule because the energy is being released inside the parcel rather than crossing the parcel boundary. So the way to think about the moist adiabatic lapse rate is that as you lift a moist parcel 1 kilometer, you get 10 degrees of cooling as a consequence of expansion, but you get 4 degrees of warming as a consequence of latent heat release. And so the overall moist adiabatic lapse rate is 6 degrees Celsius per kilometer. So again, the difference between the dry and the moist rates is explained by the latent heat release inside of the rising moist parcel. Now, what we haven't talked about is what goes on in the environment that surrounds our rising parcels. Now, in the environment, in the real world, anything can happen. So the Earth's surface can be heated by the sun as a result of energy being absorbed, and then the surface heats the air above it, and so you get warming in the surface air. Or you get the exact opposite at night as we get radiation of infrared energy to space from the surface, which then cools the air above it. And of course, the air itself can be advecting different temperature quantities or characteristics by the wind, so you can have warm advection, cold advection, and your wind directions can vary at different altitudes, and so your advections can vary as you go up through the atmosphere as well. The point is that the environment is infinitely complex, and so the environment can have any characteristic that you find at that given time and location. And so the environment is really, really complicated, and we cannot define an environmental lapse rate. So when we discuss atmospheric stability, what we're ultimately going to be doing is comparing the density of the air inside of a parcel with the density of the air in the surrounding environment to determine whether the parcel air is more or less dense, and therefore whether the parcel air is going to rise on its own or sink back to the surface. And so the environmental lapse rate can be anything. And as I go through my examples in this presentation, I'm actually going to give you specific environmental lapse rates. Remember, the environment is not a parcel. The environment doesn't have flexible boundaries. Air flows freely in the environment, so there's no restriction of where mass is and where mass isn't in terms of exchanges. And the environment is not adiabatic. So the environmental lapse rate can be anything. Luckily, the dry and the moist adiabatic lapse rates don't vary for our purposes, and they're given here as 10 and 6 degrees Celsius per kilometer of lift. So let's talk about what happens in the atmosphere as parcels rise. So in this particular example, and this is from our text, rising dry parcels cool at the dry adiabatic lapse rate. And so if we take a look at this example, we start the surface with air that has a temperature of 20 degrees Celsius, and we lift this air 4 kilometers. Now, in this example, we're going to assume that as the air rises during the first 2 kilometers of its journey, that the air is dry and it's cooling at the dry adiabatic lapse rate. So it cools from 20 degrees Celsius to 10 degrees Celsius at 1 kilometer, and then to 0 degrees Celsius at 2 kilometers. Now, we're going to assume that the air becomes saturated at 2 kilometers. And so the dew point temperature of the air inside of our parcel starts at 0 degrees Celsius. And when the parcel expands and cools to 0 degrees Celsius at 2 kilometers, this is the level at which our parcel becomes saturated. And so it transitions from being a dry parcel to a moist parcel at 2 kilometers. And we refer to this level at which a rising parcel becomes saturated as the lifting condensation level, or the LCL. And I'll have a lot more to say about the LCL when we begin to talk about thunderstorms in the atmosphere. But for now, the lifting condensation level is simply the lifting level, or the level at which rising parcel air becomes saturated, and it becomes basically the base at which we get a cloud. Now, if our parcel continues to rise from 2 to 4 kilometers, now it's saturated, it's moist, and so from this point upward, the parcel is going to cool at the moist adiabatic lapse rate, or 6 degrees Celsius per kilometer. So now you can see that the parcel cools from 0 to 6 below Celsius, from 2 to 3 kilometers, and then from 6 below to 12 below as it rises from 3 to 4 kilometers. So the parcel rises and cools at the dry adiabatic lapse rate from 0 to 2 kilometers, and then it cools at the moist adiabatic lapse rate from 2 to 4 kilometers. Now, when we talk about the environment and what the vertical temperature profile of the environment looks like, I'm going to define something called a sounding. And the sounding is really just the vertical temperature profile of the environment as we move up from the surface through the atmosphere. And we're pretty much going to just focus on the troposphere in our class. So in this particular example, we start at 20 degrees Celsius and in our environment, not a parcel, in the environment. So in the real world in this case, and this is highly simplified, but in this example, the environment is going to be cooling at a rate of 7 degrees Celsius per kilometer from the surface up to about 10 kilometers. And then what we're going to see is that from 10 kilometers to 15 kilometers, the environment is actually going to be warming at a rate of 5 degrees Celsius per kilometer. And we refer to layers in the atmosphere where we actually get warming with height as inversion layers. We call these inversion layers because the vertical warming with height is the inverse of what we typically see in the troposphere. And so we refer to lapse rates that are positive as basically normal, not normal lapse rates, but what we would expect in the atmosphere. So a positive lapse rate basically means that the temperature is decreasing with height. And it's a positive lapse rate because lapse already indicates temperature decrease with increasing altitude. And so a negative lapse rate is basically algebraically a negative of a negative. And so it's a negative of a lapse, which means that the temperature is increasing with height. And that's why our lapse rate here is negative, to indicate a positive temperature change with increasing altitude. So sounding is just the vertical temperature profile of the environment. The rate of temperature change in the environment is not a constant. So our lapse rates, our adiabatic lapse rate are constant values. Our moist and our dry rates are constants. The environment, the rate of temperature change is not a constant. So let's take a look at some real-world soundings, just so you can get an idea of what real-world soundings look like. These are Stuve diagrams. Now, you may have seen these in Geography 1250 or 1260, but what Stuve diagrams basically show is temperature along the x-axis and pressure decreasing along the y-axis. And then we have these other dashed curved lines, and we have diagonal lines, and I'm not going to talk a whole lot about them right here. But what I do want to just focus on are what we see in these Stuve diagrams. And you can see we have two curves, two black curves on our Stuve diagram. The right-hand curve is basically our vertical temperature profile as we go up through the atmosphere at this given location. And then the left-hand curve is our vertical dew point temperature profile, again, as we go up through the atmosphere at this location. And this location, by the way, is Albuquerque, New Mexico, and this Stuve diagram resulted from measurements from a radiosonde on the 2nd of April of 2022 at 12Z. In addition to our temperatures and our pressures, you can also see that we have wind information as we go up through the troposphere. And so you can see our wind directions change as well as our wind speeds change. And so this has a lot to do with wind shear, which we'll discuss in a future video. All right, so in this case, what you'll notice is that there's a large dew point depression or temperature dew point difference. And so because there's a big difference between our temperature and our dew point, the sky's going to be clear. These are going to be cloud-free conditions. And in fact, what you see over Albuquerque at this time at the surface is that the temperature was 42 degrees Fahrenheit, the dew point was 22, and sea level pressure was 1,017.2 millibars. And so you'll see that as you go up through the troposphere over Albuquerque, there's no location where the temperature and the dew point meet, so there's no location where the atmosphere is actually moist or the environment is moist. In contrast, Same date and time. This is Little Rock, Arkansas. And so if you take a look at Little Rock, and again, we have our vertical temperature profile on the right, our vertical dew point temperature profile on the left, and you'll notice that we have a fairly thick expanse of atmosphere where the temperature and the dew point are essentially the same, where the dew point depression is just about 0. And so I've circled that in right here, and so we have a small dew point depression. In other words, the temperature and the dew point are almost the same, and so you would expect that we'd have a layer of overcast over Little Rock, and that is indeed the case. The station model over Little Rock at this time shows a temperature of 50 and a dew point of 40, so you'll see that we do have some distance between the temperature and the dew point at the surface, and we have a pressure at the surface, sea level pressure, of 1,019.8 millibars. Okay, now we're going to actually just look at simple soundings in this particular video, in this particular presentation. So I'm going to take a look at 2 environmental lapse rates to illustrate how it is we determine the stability of the atmosphere. So in our first example, we're going to assume that the environmental lapse rate is 15 degrees per kilometer. So if we take a look at this particular diagram, so we have height on the y-axis, temperature on the x-axis in degrees Celsius, and we're going to assume that the temperature of the surface, of the air at the surface, is 25 degrees Celsius. Now, we know that in this case, we can determine the environmental lapse rate by just going up 1 kilometer and measuring the temperature of the environment at 1 kilometer. In this particular example, we see that the temperature at 1 kilometer is 10 degrees Celsius. So if we connect the temperature at the surface with the temperature at 1 kilometer, what we get is an environmental lapse rate line. And this basically will give us our temperature in the atmosphere at any vertical location from the surface up to 1 kilometer, but we see that the temperature decreases from 25 to 10 over this 1 kilometer vertical change, and so our environmental lapse rate is 15 degrees Celsius per kilometer. And you'll note that we drop a vertical dashed line from our temperature of 10 at 1 kilometer to the x-axis to show this 15 degree temperature decrease. Okay, so this is our environmental lapse rate of 15 degrees Celsius per kilometer. Our second example, we're going to just choose an environmental lapse rate of 5 degrees Celsius per kilometer. We're going to start again with surface air temperature of 25 degrees Celsius, but when we go up 1 kilometer through this environment, the temperature of the air is only going to decrease 5 degrees to 20 degrees Celsius. So again, if we just connect the temperature at the surface with the temperature at 1 kilometer, 25 at the surface, 20 at 1 kilometer, this is our environmental lapse rate line. And so you can see that we can determine the temperature at any location between the surface and 1 kilometer by just going along this line and looking at our altitude and dropping a line to the x-axis, and we can get our altitude and temperature. So this again shows us how temperature varies in this lowest 1 kilometer. So we're going to use these 2 examples. Now there's nothing magical about these environmental lapse rates. These are just examples. These are just assumed environmental rates. Remember, we can choose anything because the environment is infinitely complex. So let's take a look at these 2 environmental lapse rates and use them to determine the stability of the atmosphere. So again, the vertical dashed line indicates the temperature in both examples at 1 kilometer. Now, how do we determine the stability of the atmosphere given our dry adiabatic lapse rate, our moist adiabatic lapse rate, and our environmental lapse rates? So we're going to keep things really simple, but I want you to remember this basic flow chart in words of how it is we determine atmospheric stability. You're going to be expected to know this moving forward when I actually give you exams in our class for exam 2 and the final exam. So to determine the stability of the atmosphere, number 1, you're going to place a parcel at the surface. You're going to assume that the air inside the parcel has the same characteristics as the air in the environment at the surface. So the air inside the parcel is going to have the same temperature and dew point as the air in the surrounding environment at the surface. We're then going to take our parcel and we're going to lift it from the surface to 1 kilometer. And then what we're going to do is we're going to compare the parcel environmental temperatures at 1 kilometer. And so while we compare temperatures, we're also going to do a comparison of densities, assuming that the parcel pressure inside of the parcel is identical to the pressure of the atmosphere at 1 kilometer. So if the temperature of the air inside the parcel at 1 kilometer turns out to be colder than the temperature of the environment at 1 kilometer, then the air inside the parcel is going to be more dense than the air in the surrounding environment, and because the air is more dense, the parcel is going to sink to the surface. So just imagine that you take a ball, a baseball or basketball, and you toss it up into the air, and then you just stop the ball at that level where it just reaches its highest altitude, and you do a comparison of the ball with the surrounding environment. And what you're going to find is the ball is going to be more dense, and so it comes right back down to the surface again. So this is an example of stability, going all the way back a couple of slides to where I had that tennis ball inside the depression. So you throw that parcel up into the air, the parcel returns to its initial position, and so we have stable. All right, so again, if you lift the parcel to 1 kilometer and the air inside that parcel at 1 kilometer is colder and more dense than the air in the surrounding environment, the parcel is going to come back down to the surface, it's going to return to its initial position, and so the atmosphere is stable. On the other hand, if you lift the parcel 1 kilometer, and then when you do your temperature comparison, you find that the air inside the parcel is warmer than the air in the surrounding environment, then the parcel air will be less dense than the environmental air, and as a result, the parcel, which is relatively buoyant, will accelerate upward from that 1 kilometer position. In this case, because the parcel is accelerating away from its initial position after being displaced upward, we'll say that the atmosphere is unstable, which gets back to our definition from a couple of slides ago. We displace the parcel upward from its initial position. The parcel then accelerates on its own away from its initial position, and so the atmosphere is unstable. So the atmosphere will be unstable when, after displacing the parcel upward, the parcel becomes warmer and more buoyant than the surrounding environment. Finally, if after displacing the parcel upward 1 kilometer, we find that the parcel and the environmental air have identical temperatures, then the parcel and the environmental air will have equal densities, and the parcel will just remain at 1 kilometer. It will just remain at that level where it's been displaced. So the parcel remains at 1 kilometer, and we say that the atmosphere is neutral. I want you to learn and remember this slide. It's an important slide. Okay, so let's move back to our examples. So we're going to go back to our environmental lapse rate of 15 degrees Celsius per kilometer. So what I'm going to do is I'm going to again draw a height temperature diagram, or a temperature height diagram. Here's our environmental lapse rate of 15 degrees Celsius per kilometer. Now what I'm going to put on this diagram is what I call, or what is called, a dry adiabat. So what a dry adiabat does is it shows you the temperature as I go from the surface to 1 kilometer, the temperature of the air inside of a rising dry parcel. Now remember, the dry adiabatic lapse rate is 10 degrees Celsius per kilometer. So when we lift a dry parcel through this environment, the air inside the parcel is going to cool from 25 degrees at the surface to 15 degrees, at 1 kilometer. So it's going to cool 10 degrees as you lift it 1 kilometer. And so our dry adiabat basically shows us the temperature inside of our dry parcel at any location along this vertical path from the surface to 1 kilometer. So the blue line is a dry adiabat, and it just shows us our dry adiabatic lapse rate inside of our rising dry parcel. The black line is the environmental lapse rate, and what we see after we lift our air that's dry 1 kilometer, at 1 kilometer when we do our comparison, we see that the temperature inside of our dry parcel falls to 15 degrees Celsius, while the temperature in the surrounding environment is 10 degrees Celsius. So 1 kilometer, the air inside of our dry parcel is warmer than the air in the surrounding environment, so the parcel air will be warmer, more buoyant, and it will rise up on its own. So at least when the air is dry, the atmosphere is going to be unstable. Well, what about when the atmosphere is moist? So let's see what happens when we have a moist parcel. So you'll note again, we have exactly the same environmental lapse rate line. It's no different. The environmental lapse rate remains 15 degrees Celsius per kilometer. But now what we're going to do is we're going to assume that the air at the surface is moist, that the relative humidity is 100%, and we're going to lift our moist parcel 1 kilometer. Now this red line is what we call a moist adiabat. So what the moist adiabat does is it maps the temperature inside of our moist parcel as it rises from the surface to 1 kilometer. And what we'll see is that because the moist adiabatic lapse rate is 6 degrees Celsius per kilometer, that the temperature inside of our rising moist parcel will decrease from 25 to 19 degrees as it cools those 6 degrees on its way up to 1 kilometer. So now the red line is a moist adiabat, the black line is the same exact environmental lapse rate line of 15 degrees Celsius per kilometer that we have in our top diagram. Now what you're going to note is that at 1 kilometer, the moist parcel is 19 degrees Celsius, and in fact, the moist parcel at 1 kilometer is going to turn out to be 4 degrees warmer than the dry parcel at 1 kilometer, and that 4-degree difference is a consequence of the latent heat that's released as our moist parcel rises. So again, there's that 4-degree difference between our dry and our moist adiabatic lapse rates that's explained by the release of latent heat inside of rising moist parcels. And so what you see now is that our moist parcel is 19, while the temperature inside in the surrounding environment is 10. So the moist parcel is even warmer at 1 kilometer than the dry parcel. And so what we see is that regardless of whether the air is dry or moist, in this environment where the environmental lapse rate is 15 degrees Celsius per kilometer, the atmosphere is unstable. Both dry and moist parcels will accelerate upward from their initial position after they're lifted because they become warmer than the surrounding environment. So it turns out that we can actually define the conditions that describe instability in the atmosphere. And that condition is that the environmental lapse rate has to be greater than the dry adiabatic lapse rate. In other words, the environmental lapse rate has to be greater than 10 degrees Celsius per kilometer. When the environmental lapse rate is greater than 10 degrees Celsius per kilometer, what we see, and we see it up here on our top diagram, is that after lifting a dry parcel, the dry parcel will end up being warmer than the environment and will accelerate up on its own. Now, the condition for instability involves an inequality of our dry adiabatic lapse rate, because if a dry parcel is warmer and more buoyant after being lifted, the moist parcel has to be even warmer and more buoyant than the dry parcel at that altitude because of the latent heat release. So all we need to do is ensure that the atmosphere is unstable when it's dry, and what we'll find is the atmosphere will be even more unstable when it's moist because of the additional energy that is put into that parcel as a result of latent heat release when vapor condenses to form a cloud inside of our parcel. So this is our condition for instability in the atmosphere. The environmental lapse rate has to be greater than the dry adiabatic lapse rate. Now let's consider the example where we take our environmental lapse rate and we define it to be 5 degrees Celsius per kilometer instead of 15 degrees Celsius per kilometer. So in this case, what you see is that the rate of cooling in the environment is much smaller than it was in our previous example. So you have to go up a kilometer in the environment to get a cooling of only 5 degrees Celsius. So what we're going to do is we're going to just do what we did in our last example, is we're going to first add a dry adiabat, and note that the dry adiabatic lapse rate doesn't change from example to example. The dry adiabatic lapse rate is always going to be 10 degrees Celsius per kilometer. So now what we see is that when we lift our parcel along a dry adiabat, so we take our parcel and we assume it's dry, so it's cooling again from 25 degrees Celsius at the surface, 10 degrees to 15 degrees Celsius at 1 kilometer, then what we see now is that the parcel, which has a temperature of 15 degrees Celsius at 1 kilometer, now ends up being colder than the environment, which cooled only 5 degrees from 25 to 20. So at 1 kilometer, the parcel is going to have a temperature of 15 degrees Celsius. The surrounding environment is going to have a temperature of 20 degrees Celsius. And what we're going to see now is that the parcel is colder than the surrounding environment. So again, the blue line is our dry adiabat, the black line is the environmental lapse rate line, and we see that the parcel ends up being colder in this case than the environment of 1 kilometer. Now, let's take a moist parcel and lift it 1 kilometer. So we take our parcel and we lift it 1 kilometer, it's going to cool along a moist adiabat, and so the moist adiabatic lapse rate, remember, is 6 degrees Celsius per kilometer. Our environmental lapse rate is 5 degrees Celsius per kilometer, so the rate of cooling in our parcel is just a little bit greater than the vertical rate of cooling in the environment. And so what we see at 1 kilometer is that the parcel, which still cools from 25 to 19 when it's moist, ends up being just 1 degree colder than the environment, which cooled from 25 to 20. Now in this case, there's only a small difference in temperature, 1 kilometer, between the parcel and environment air. But the air inside of the moist parcel is still colder than the air in the surrounding environment, and so it's still going to come down to the surface. And so we're still going to have stability because at 1 kilometer, our moist air is still going to be colder and more dense than the air in the environment. So again, our red line is the moist adiabat, our black line is the environmental lapse rate line. And what we see in this example is that the atmosphere is stable. It doesn't matter whether we're lifting a dry parcel or a moist parcel. After we lift those parcels 1 kilometer, we find in both cases that the parcel air will be colder, more dense in the surrounding environment, and so the parcels are going to come down regardless of whether they're dry or they're moist. So the atmosphere is stable. Now, what you'll notice in this case is that while the atmosphere is stable, it's a much closer call when the parcel is moist than when the parcel is dry. So in order to define stability in the atmosphere, in order to give the condition that explains stability in the atmosphere, we're going to give another inequality here. I'm going to put down another inequality, and this inequality is going to compare the environmental and moist adiabatic lapse rates. Because of the latent heat that's released inside of rising moist parcels, if moist air after being lifted still ends up being colder than the environmental air and we have stability, then we can be certain that dry air that starts with the same surface conditions is going to be even colder and more stable. So if after lifting and having latent heat release, our moist parcels are colder and more dense and they come down, we don't need to worry about our dry parcels. If the moist air is stable, the dry air is going to be even colder at 1 kilometer and even more stable. So the inequality that we use to define instability in the atmosphere is that the environmental lapse rate has to be less than the moist adiabatic lapse rate. So if the rate of cooling in our moist parcel is greater than the rate of cooling in the environment, which is what we have in this bottom figure here, if the rate of cooling in our moist parcel is greater than the rate of cooling in the environment, then the moist air at 1 kilometer will be colder, more dense, and will come back down, which is stable. And then, of course, the dry air will be even colder because there's no latent heat release, and so this dry air is certainly going to come down. So this is the condition that we provide to define stability, not instability, stability in the atmosphere. Now, I've given you unstable and I've given you stable. Now, it turns out there is a middle ground where we can actually have an environmental lapse rate that falls somewhere in between our dry and our moist rates. And so I give it to you right here. In this case, the environmental lapse rate we're going to define to be 8 degrees Celsius per kilometer. So it's smaller than the dry adiabatic lapse rate, but it's larger than the moist adiabatic lapse rate. So what is the stability of the atmosphere in this case? Well, it turns out the stability of the atmosphere is a little bit of both. So let's take a look and see what happens. So our blue line is our dry adiabat, our red line is our moist adiabat, and our black line in this case is an environmental lapse rate of 8 degrees Celsius per kilometer. We refer to this condition where the environmental lapse rate in terms of its value is somewhere between the moist and the dry rates. We refer to the atmosphere as being conditionally unstable. Now, if you take a look at what happens, let's just start at the surface and assume that our air is dry. So if our air is dry, then the parcel is going to cool when we lift it at the dry adiabatic lapse rate. So we're going to go up our blue dry adiabat, and we see that the air in the parcel cools from 25 to 15 degrees at 1 kilometer. Now the environmental lapse rate is 8 degrees Celsius per kilometer. So if we go up through the surrounding environment, we see that the air is going to cool from 25 to 17. It's going to cool 8 degrees as we go up from the surface to 1 kilometer. So the air in the parcel is going to have a temperature of 15 degrees at 1 kilometer. The air in the environment is going to have a temperature of 17 degrees at 1 kilometer. So the dry air at 1 kilometer is going to be colder and more dense in the environment, and so the dry parcel is going to come back down to the surface, stable. Now, if we assume that the air at the surface is saturated or moist, then when we lift a parcel, that parcel is going to have to go up a moist adiabat. And so the parcel is going to cool from 25 to 19 degrees. I gave the condition, I want to take that back off again. The parcel is going to cool from 25 to 19 degrees. It's going to cool 6 degrees. And so if we compare the air inside the moist parcel at 1 kilometer, which has a temperature of 19 degrees, with the air in the surrounding environment, which has a temperature of 17 degrees, what we see now is that the moist air is warmer than the environment air. And so the air inside the moist parcel is not going to be just warmer, but it's going to be more buoyant, and the moist air is going to accelerate up on its own. So this is unstable. So what we see is that the atmosphere is both stable and unstable, depending on whether the atmosphere is dry, stable, or moist, unstable. So we refer to the atmosphere now as being conditionally unstable. And I'm going to put down another inequality to define conditional instability in the atmosphere. But what we find with conditional instability in this case is that the moist adiabatic lapse rate has to be less than the environmental lapse rate, which has to be less than the dry rate. So what we see is that when the environmental lapse rate is less than the dry adiabatic lapse rate, dry air will be stable and will come back down. But when it's greater than the moist rate, the moist air will be unstable, it'll go back up on its own, and so we basically have instability when the atmosphere is moist or saturated. And so this is conditional instability, and the condition for instability is that the air has to be moist for the atmosphere to be unstable. Now before I move on from comparing lapse rates, I want to make one thing really clear about how it is you determine stability when you take a look at these diagrams. And this is a common mistake that students make that I want to stop you from making right here at the onset. When we compare parcels and the environment, parcels are only going to cool at one of two rates. They're either going to cool at the dry rate or the moist rate. And so when we lift our parcels to determine what the air temperature inside the parcels will be, we lift our parcels either along a dry adiabat, when we assume the air inside the parcel is dry, or a moist adiabat, when we assume that the air inside the parcels is moist. We never lift a parcel along an environmental lapse rate line. Parcels do not cool at the same rate as air in the environment, unless it so happens that the environmental lapse rate is identical to one of our adiabatic lapse rates. And I'm not going to give you those examples. I want to keep it more clear cut. So just remember that dry parcels cool along a dry adiabat as you lift them, and moist parcels cool along a moist adiabat as you lift them. Okay, let's keep going. So in general terms, to determine the stability of the atmosphere, you always start by just drawing your dry and your moist adiabat. The dry adiabat is always going to have a lapse rate of 10 degrees per kilometer. The moist adiabat is always going to have a lapse rate of 6 degrees per kilometer. So in this particular example, I've drawn a diagram, and in this case, I've assumed that the surface temperature is 35 degrees Celsius. Remember that when we begin lifting our parcels from the surface, by definition, the rules that I gave you a couple of slides ago, the temperature and humidity characteristics of the air inside the parcel will be identical to the temperature and humidity characteristics of the air in the environment at the surface. And so you always lift along a dry adiabat from the surface, from a moist adiabat along from the surface, if you assume that the air inside the parcel is dry or moist. So the dry air will cool by 10 degrees Celsius to a temperature of 25 degrees Celsius at a kilometer, and the moist air is going to cool from a temperature of 35 degrees to a temperature of 29 degrees at 1 kilometer, assuming that the dry parcel cools 10 degrees Celsius as you lift it 1 kilometer, and the temperature inside the moist parcel cools 6 degrees as you lift it from the surface to 1 kilometer. So then, to determine the stability of the atmosphere, you then put in the environmental lapse rate line, and you won't know what the environmental lapse rate line is going to be until I give it to you. And so that's always the question mark with these figures. So here's an example of an environmental lapse rate line where the environmental lapse rate, the temperature in the environment is going to fall from 35 to 23. Now I'm gonna just give you some questions, and I want you to do these offline on your own. So you can basically just stop the video and then answer the following two questions. What is the environmental lapse rate? And I'm giving you some multiple choices here. So it's either going to be 6, 10, or 12 degrees Celsius per kilometer. And then given the environmental lapse rate, is the atmosphere stable, conditionally unstable, or unstable. So what you need to do to determine this is you need to take parcels and lift them up with a dry adiabat and then a moist adiabat. Follow the instructions I gave you earlier in the presentation. Compare temperatures, just do a temperature comparison of 1 kilometer, and then do your density comparison to determine whether dry parcels, moist parcels go back to the surface, stable, or accelerate upward, unstable. Okay, here's another example with a couple of more multiple choice questions. Again, same dry and moist adiabats, but a different environmental lapse rate. So in this case, between the surface and 1 kilometer, environmental temperature is going to fall from 35 degrees Celsius to 31 degrees Celsius. So you're going to be asked now what the environmental lapse rate is. It's either going to be 4, 6, or 10 degrees Celsius per kilometer. And then given that environmental lapse rate, you're again going to lift dry and moist parcels, and then at 1 kilometer, you're going to do your temperature and density comparisons to determine whether the dry and moist parcels go back down to the surface, stable, or rise up on their own, unstable. So for this example, is the atmosphere stable, conditionally unstable, or unstable? And then finally, I'm going to give you an example where the temperature in the environment decreases from 35 to 27 degrees Celsius. And then given this, you're going to have to determine the environmental lapse rate, and one last time, determine whether the atmosphere is stable, conditionally unstable, or unstable. All right, so I'm going to want you to do those, and I will give you those answers at some point, either if this is a classroom, if this is a face-to-face class, we'll discuss it in class. If this is a distance class, if this is eCampus, I'll give it to you in a little Canvas quiz. All right, now let's move on to a little bit more of the real weather. So here is a nice video or a nice picture of cumulonimbus clouds that I kind of shamelessly stole from the internet. But this is a really nice picture of the types of clouds we see when the atmosphere is unstable, when we have instability in the atmosphere. So when you see cumulonimbus clouds of this sort, this indicates instability in the atmosphere. So we're talking about environmental lapse rates that are large. Now, in reality, we don't usually see unstable conditions in the atmosphere. We'll typically get thunderstorm activity in an atmosphere that is conditionally unstable. So we'll have environmental lapse rates somewhere between 6 and 10 degrees Celsius per kilometer and high humidity values in the atmosphere, so a lot of vapor in the atmosphere. So cumulonimbus clouds, and cumulonimbus indicates that these clouds are actually producing precipitation. That's the nimbus part. They reflect atmospheric instability. We usually have intense updrafts in these clouds, and so we get cloud level latent heat release. So there's a lot of condensation going on in these clouds, and so as we get vapor condensing, we get our latent heat release, and so we have moist parcels rising and latent heat release. But we also, in cumulonimbus clouds, as you know with thunderstorms, you also have intense downdrafts. And so we typically will have heavy precipitation, rain, hail, and so as we get this heavy precipitation, we often get surface cooling. As a matter of fact, we almost always get surface cooling, and this surface cooling is a result of downdrafts that are actually cooling down colder air, where we have rain actually evaporating in the air beneath the clouds, or we actually have cold cloud level air being pulled down to the surface as well. So thunderstorms typically cool surface air. So here is a really simple panel from a meteogram. It's an old one from the Texas from the 5th and 6th of August of 2002. You can see at this location we have a hot day. Temperature is rising through the 90s until about 20 Z in the afternoon. And then this location has a thunderstorm. So you can see thunderstorms being reported at 21 and 22 Z. And you can see the temperatures kind of plunging from around 95, 96 degrees down into the upper 70s to about 76, 77 degrees. So you can see our temperatures take a big plunge, almost 20 degrees during this thunderstorm activity, with our dew points coming up a bit. So the thunderstorms actually cool the surface air. Now, if you think about surface air cooling, what that actually does is it causes our environmental lapse rate to decrease. So we're cooling the air at the surface, and if you assume that there's not much change in the temperature of the air in the environment at 1 kilometer, this cooling of surface air is going to cause the rate of cooling, the vertical rate of cooling in the environment to decrease. And so thunderstorms actually cause our environmental lapse rates to decrease, and that causes the atmosphere to become more stable. And so when we talk about thunderstorms in our future videos, we're going to see that the atmosphere actually becomes more stable as a result of a thunderstorm actually causing rain to fall. I'll also note that thunderstorms can actually lead to cloud level warming as a result of latent heat release. So as we're getting cooling at the surface, we can also have some warming occurring at cloud level. And that also causes our environmental lapse rate to decrease. So just imagine that you get cooling at the surface and warming at the upper levels, and that actually causes our environmental lapse rate line to become less diagonal and more vertical, so that our environmental lapse rate is decreasing quite a bit. So latent heat release at cloud level, as we get our clouds and our precipitation forming, can also make the atmosphere more stable. Now, in addition to the atmosphere being stabilized as a result of latent heat release at cloud level and cooling at the surface, we actually also can find that we can get thunderstorm activity as a result of large-scale cooling at upper levels. And so we actually can see instability or destabilization of the atmosphere as a result of an approaching short wave or long wave trough causing cooling of cloud level air. So we get lower heights, cooler air, and so if we get cooling air at upper levels and not much change at the surface, that will actually cause our environmental lapse rate to increase and destabilize the atmosphere. So as we get approaching troughs at upper levels, we can actually get cooling at upper levels, which causes the environmental lapse rate to increase and can cause the atmosphere to become more unstable. So here's an example from our book, and in this case, what we have is a long wave trough actually approaching the west coast of the United States, and really cold upper level air associated with that trough. And so in this case, we're actually not looking at isolated heights, but we're actually taking a look at 500 millibar temperatures. And so you can see they have 500 millibar temperatures that range from about 12 below 0 Celsius on the very southern edge of the map over the Pacific. The temperatures as cold as 32 below 0 in the base of the trough off the coast of British Columbia. And so we have really, really cold upper level temperatures. And if we take a look at a visible satellite image from the same time, this is from 2004, what you'll notice is we have a lot of extensive cloudiness extending from our low over the Pacific. Here's our cold conveyor belt over the Pacific Ocean, warm conveyor belt just over Vancouver Island and British Columbia, and then you can see our cold front that's actually inland over the Pacific Northwest, going from Washington through Oregon, Nevada, and then into Northern California. Now what you'll notice in the dry conveyor belt air over the Pacific Ocean is that we actually have a lot of cloudiness. So we have a lot of splotchy cloudiness. This is actually convective cloudiness, where we have really, really cold air at 500 millibars over the much warmer waters of the Pacific Ocean. And so as a result of having warm surface air temperatures and very cold upper air temperatures, we have very large environmental lapse rates. And so what happens as this cold air associated with the trough moves over this much warmer water is we end up getting convection and thunderstorm activity, convective activity over the ocean itself. And so what you're seeing here in this area that would typically be dry conveyor belt air is we have actually a lot of thunderstorm activity popping up as a result of this warm surface air and much colder upper air moving over this warm surface. So the approaching shortwave, long wave trough cools cloud level air. Our environmental lapse rate increases because we have warm surface air and the atmosphere becomes more unstable. And again, you can see this very convective looking cloudiness over the Pacific where we have our instability. So one last topic that I want to talk about before I end the video, and this is actually going back to large scale surface high pressure. So remember, as a result of increasing vorticity, we get upper level convergence, which increases the mass of the column, and we get surface high pressure. With our surface high pressure, we get downward motion, and so we get deep layer subsidence, which if we have convection just above the surface as a result of intense surface heating from the sun, this deep layer substance will cap the convection and will lead to something called a subsidence inversion. So if we take a look at this image, which again is from our text, you'll see we have this large scale subsidence, and what it's doing is it's basically quashing the convection that we're getting just above the surface as a result of intense surface heating and large environmental lapse rates. And if we take a look at the sounding on a day when we have a subsidence inversion, what you'll notice is that we have, I'm getting OneDrive being verified right now, what you'll notice is we have large environmental lapse rates from the surface up to about 850 millibars in this particular example. And then we have this little bit of a substance inversion indicating that we have temperatures increasing for a little bit of vertical distance, and then we have temperatures decreasing with height through the rest of the depth of our troposphere. So let's take a look at an example of how it is we actually get a substance inversion. So here's an example of, and I can tell you exactly where this is from. This is actually from Penn State. We are looking at University Park from one side of Atherton Street. We're crossing Atherton Street. Here is Walker Building, right here is this little white building, and here is the smokestack from the power plant. And Mount Nittany is off in the distance. And if you take a look at these two little light green lines, if you notice that, this is Tussey Mountain Ski Resort, and this is where Samuel skied for the first time in his life many, many years ago. So this is kind of a nostalgic image for me, but I'm going to ruin the nostalgia and talk about substance inversions. Now, I want you to notice that we do have cloudiness in the sky over Penn State and State College on this day, and this is very shallow convection. So we have convection going on as a result of intense surface heating and large environmental lapse rates just above the surface. But you'll notice that these cumulus clouds are very shallow. They're being quashed or squashed. And that's because we have large-scale subsidence and the substance inversion right above these cloud tops. And so let's take a look at what might be happening on this day. So imagine that we have a layer of air from 3 to 400 millibars, and that is this blue square right here. So this is a 100 millibar thick layer of air. So we have basically 300 millibars at the top, 300 and 400 millibars at the bottom. And what we're going to do is we're going to take this air and we're going to drop it from 300 to 400 millibars, and we're going to keep the layer of air 100 millibars thick, but we're going to drop it all the way down 400 millibars so that this layer is now between 700 and 800 millibars. Now what you're going to notice is that because pressure decreases exponentially with height, there's a really big vertical distance from 400 to 300 millibars. So you'll see that the 400 millibar level is at about 7,000 meters, and the 300 millibar level is more than 9,000 meters. So this is like a 2,200 meter difference or thick layer from 4 to 300 millibars. If we take this layer of air and we bodily bring it down so that it's between 7 and 800 millibars, what you'll notice is that the top of our layer, which is going to drop from 300 to 700 millibars, is actually going to fall further vertically than the bottom of our layer, which is going to move from 400 to about 800 millibars. And so what we see is that the top of the layer is going to fall further than the bottom of the layer. Now, so 300 to 400 millibars is going to sink from 700 to 800 millibars. Well, let's talk about what happens to the temperature of the air at the top of our layer and the temperature of our air at the bottom of the layer as we take this layer and we drop it. So again, air originating at 300 millibars is going to sink further than air originating at 400 millibars. And you can see this really clearly. And now this is a result, again, as a result of the exponential decrease of pressure with height, or the exponential increase as we go back down towards the surface. And so in meteorology, we assume that all air, whether it's moist or dry, as soon as we begin to bring it down, we assume that as a result of compression and warming, that all sinking air warms dry adiabatically. And so because the air at 300 millibars is going to fall further as it goes to 700 millibars than the air at 400 millibars as it drops to 800 millibars, the air at the top of the layer is going to warm more than the air at the bottom of the layer. And that's going to lead to a substance inversion. So we're going to get warming more at the top than the bottom. And so as we go up through our green layer, we're going to see temperature increase with height. And so we get a subsidence inversion forming. And again, you can tell we have a substance inversion because we have these cumulus clouds, but their vertical extent is really, really shallow. They can't rise far. Inversions are extremely stable. And so air can't rise through inversions, and so that caps the top of their clouds. Okay, so that is pretty much the end of my lecture for today. The lab questions for our face-to-face meeting are questions 1 through 3, 5, 6A through E, 7, 9 through 11, and 13. And we have no figures for our lab assignment this week, so there's no need to do a PDF file for me this week. Okay, so that's everything I'm going to say about Chapter 8. Long video. I'm going to end it. It's going to take a while for it to upload to YouTube, but as soon as it's uploaded, I will post an announcement so you can watch it. And again, for those of you who are taking this face-to-face, I want to make sure that you watch this before our next class meeting. And that's everything. So let me just end the video now.